Hello, I'm Andrew Lincowski, and I'm here presenting to you about TRAPPIST-1 planetary simulations with a multi-column climate photochemistry model. I think an important consideration for our modeling efforts is to consider that photons are coming. We actually have telescopes launching and being built this decade that will be able to observe potentially habitable environments in the habitable zones of their host stars, particularly around M-dwarf stars. Our numerical climate models can assist this in a number of ways, some of which have been working on for a number of years. We've been long making testable predictions that we can now assess with James Webb and other telescopes. But we have to understand how we can best utilize these predictions into an observing strategy that considers the high cost and difficulty in obtaining telescope observations. These could include different band passes, the number of transits, etc. These models can also be used in retrieval frameworks to constrain the temperature structures or gas abundances of key spectrally visible gases, and in particular aid data interpretation when we do have these constraints and have to explain how these gases can exist and whether the planet may be habitable or inhabited. 1D and 3D climate models have complementary characteristics that can aid in these various aspects that I hope Samantha Gilbert in her talk has shed light on as an introduction to this. To bridge these 1D and 3D model advantages, I've developed a two-column model for synchronously rotating planets. Before I talk about the two-column model, I'd like to introduce the one-column model underpinning this work, which is the VPL climate model developed recently. Now, this is really not your Grandpa Jim Casting's 1D model that's been in use for the last several decades. This model wraps a versatile line-by-line, multi-stream, multi-scattering radiative transfer model, SMART, which has been around for a while. For convective processes, we do not use convective adjustment. We use mixing length theory, which helps determine the vertical mixing rate in a physically consistent manner and includes condensation of key vertically mixed gases, particularly water vapor, but also other gases such as sulfuric acid, which is in Venus's atmosphere. Now, this model is capable of a wide variety of environments. It's been validated for Mars, Earth, and Venus by Robinson and Crisp in 2018, and has subsequently been used in a wide range of planets from oxygen-dominated to Venus-like to Earth-like, and is now being used also for hydrogen envelope planets like super-Earths. To calculate horizontal heat transport to connect the day and night sides of this model, I do not include an analytic formulation like some of the recent exoplanet models have used. Instead, I've looked at the meteorological primitive equations, such as those used in GCMs, and have distilled it into a framework that works for a two-column model. In particular, this model will calculate both the horizontal zonal wind speeds and vertical wind speeds to get a self-consistent solution. But I'd also like to point out that both the GCMs and this framework must inevitably include the diabatic heating, which is calculated by radiative transfer and latent heat exchange. And so the diabatic heating can affect the dynamics and therefore impact the structures of the planet. To validate this model, I've obtained data from Eric Wolf from his TRAPPIST-1 intercomparison model for the Ben 2 1-bar CO2 case. You have temperatures on the left and the horizontal wind speed on the right. The gray region demonstrates the entire range of profiles for the planet and all the latitude and longitude points. And the dashed lines represent the averages. In the temperature, you have the night side average in blue and the day side average in orange. And then you have just the global average for wind speeds on the right. I've also included the two-column results as well. And what you can see is that on the right, we'll start with the horizontal wind speeds are coarsely reproduced by this model framework. The relative magnitudes are roughly the same, even if the actual shape is different. But what this really demonstrates is the general qualities of the hemispherical averages. On the left, you can see that below about 0.5 bar, the temperatures diverge towards the surface, similarly for both models. And above the 0.5 bar region, you have the hemispheres are roughly averaged together. So you have basically the weak temperature gradient being demonstrated there. And though it is good to see that these features are reproduced by the two-column model and similar to the GCM, even if the actual profiles of the atmospheres are a little bit different, which may owe to either the diabatic heating or the calculation of dynamics. Most particularly, GCMs have pointed out for years the importance of the day-night surface temperature contrast. So we've compared that here between the climate model that I've produced and the GCM for comparison. And you see that we're within about 10 to 15 Kelvin at the surface of the hemispherical average. It is a little bit higher, but it's also much lower than the minimum to maximum of the GCM. So it's good to be within the range that the GCM exhibits for the day-night average. So we consider this a success as well. But now we can go past the surface contrast and look at the climate profiles, but now we have a variety of different atmospheres. We have our intercomparison atmospheres on the left, where you again see the temperature divergence from about the middle troposphere towards the surface. We have some photochemically mediated atmospheres in the center with a similar behavior. And then on the right, we see evolved environments that have much thicker atmospheres, and you actually find that thicker atmospheres are pretty well approximated by 1D models because the thickness of the atmosphere and its heat capacity ends up producing a much smaller difference towards the surface. To relate these modeled environments to observations that may be made in the next 10 years, we have to consider the main modes with which James Webb will be observing these planets. And those two are going to be transit spectroscopy and eclipse spectroscopy. Eclipse spectroscopy may probe the thermal structures of the atmosphere, but my colleague Jacob Lustig-Jaeger in a paper last year has shown that the number of occultations or transits required to do so is quite high compared to transit spectroscopy. In this plot, this is the number of occultations to detect the atmosphere. So it'll be very difficult, even for hot planets, to even detect an atmosphere with the secondary eclipse spectroscopy, whereas transit spectroscopy is much more versatile and applicable to the temperate planets that we're observing. So really, transit spectroscopy is the only method for characterizing temperate terrestrial atmospheres in the next decade with James Webb. Now, the region of the atmosphere that transmission spectra probe is an important consideration in what type of modeling framework and where you spend your efforts on tying to observations. This really probes the photochemical or radiative region of the atmosphere. You see on the right that where the temperature diverges towards the surface is well below the region of the atmosphere probed by transit spectra. The region probed by transit spectra is in the levels above the 0.5 bar region, really towards the upper troposphere and into the stratosphere, where the planetary temperatures are really well recommended by a 1D model because the temperatures are have a low gradient there. Now, if we compare some of our two-column results to the GCM again, and this is the HAB1 case, the aquaplanet, we find that the effects are really quite small, and in fact, the planet is pretty well modeled by either model. The differences between the average of the transit spectra around the terminator for the GCM are pretty close to that calculated by the two-column model. Their primary difference is due to where the clouds are located, which are prescribed in the two-column model but calculated in the GCM. And when you consider that in a model retrieving framework, for like the plot on the right, is you're not going to a priori know where your cloud deck is. You won't be able to distinguish a surface from the cloud deck or a refraction limit. And so you're considering just the atmospheric features above your continuum. And when you place these models together, the water features are really well within the error bars, very similar to each other. And so these effects will be very difficult to distinguish between the 1D results and the 3D results, despite the fact that their surface temperature, or that their temperature profiles were actually significantly different. Now, other types of observations we might make might include phase curves. Typically, GCMs will demonstrate bolometric flux phase curves, but these cannot really be observed. You can only observe in particular wavelength bands with James Webb. So you have to consider that you have to carefully choose one or more bands to observe your planet in, and that you have to be considering the atmospheric composition of your planet. For example, here the 12 micron band has quite a strong flux compared to the others. But if you look at other types of atmospheres, that might not be the case. Here we're looking at a Venus-like or an oxygen-dominated planet, and you actually find that the 12 micron band is relatively small for both of those planets. But you have other bands, maybe more towards the 10 micron region, but especially the 15 and 20 micron region, where the atmospheres are very different and very different than an Earth-like planet. So when you consider not just how you may optimally observe the planet you're hoping to see, an Earth-like planet, it's also important to consider the diversity of planets that may exist and how they may present differently in the types of bands that you may observe in, particularly the 15 micron band for CO2. I hope I've demonstrated in this talk that a modern two-column model has capabilities that bridge both 1D and 3D models. On the 1D side, it employs key photochemical processes that can alter the stratosphere and give you trace gases that may not be present in GCMs, and also includes versatile radiative transfer physics that allows you to model a vast variety of atmospheres. Now, in considering the 3D GCM advantages of your day-night surface temperature contrasts, a two-column model does well produce the day-night contrast, and you may be able to assess whether collapse on the night side occurs for a given atmosphere. We can also use this data to produce thermal phase curves and day-night phase amplitude variation spectra to assess some of the James Webb secondary eclipse observations, which, while not possible for temperate planets, may be quite useful for hotter planets that could be Venus-like. Particularly amongst all these models, transmission spectra for James Webb are sensitive to photochemically mediated gases and are really not sensitive at all to day-night surface temperature differences. And what this means is that versatile 1D coupled climate photochemical models are ideally positioned to predict and interpret these types of spectra for upcoming transit observations with James Webb. Looking towards the future, 3D GCMs may better inform observations of direct imaging, such as that might be conducted by LUVOIR. Thank you.